Okay, thank you. Okay,
Oh, I did have one more question. Is there an assignment for the sunscreen lab?
01.
Place to submit the sunscreen lab.
That was lab 6. Okay, let me see. Let me jump over to,
He added it on Canvas.
Okay, thank you.
oh, all right, good. I was about to jump over to Canvas there. Okay, so this chapter, as I was saying, is on energy. And the issue with energy in the body, it's has to be done at a super low temperature. But and it also has to be stored. So there's a lot of kind of complications because we're a living being. And because of that, our body does it all with the magic of enzymes, which can function at pretty low temperatures. There is no lab next week, so we don't have a pre-lab write-up for next week. So I'm assuming that's what your question was about. Okay. Now, probably from 305, you talked about energy, and energy is, this statement isn't entirely correct. It can be interconverted, though. Using this relationship here. So it can be converted from one form to the other. In other words, this would be potential to kinetic energy. And then either one of these can be converted to mass. Now that doesn't happen in our body, but I just want to make sure you understand this statement isn't quite true. Okay. Now the energy path goes sun to organisms that use the sun to generate molecules. And those molecules then store potential energy in bonds. And then we can utilize those molecules and interconvert the bonds into useful energy. Which this slide talks about. Okay, here's an organism that converts, uses sun and carbon dioxide to produce molecules that have potential energy stored in their bonds. And then we can utilize those molecules to do things like mechanical work, which is temperature. We can also use it to we can use that to make molecules for energy storage. And all of you know those are, main one is ATP, which then can be stored via numerous things. Okay, it's stored via fat in the form of triglycerides. It can be stored in no, let's see. Carbohydrate in the form of glycogen. And in the form of proteins. Okay, and we utilize this first the glycogen, then the fat, then protein. In terms of if we were starving, for example. Okay, so now this relationship you might not have had in 305. This is entropy. This is enthalpy. And this is now the G is much more accurate at determining reaction spontaneity. In other words, does a reaction go? Entropy is temperature dependent. As temperature goes up against the entropy constant for that reaction, the reaction will get more negative. Okay, so if delta G is less than 0 or negative, it's considered a spontaneous reaction. If delta G is greater than 0, it's not a favored reaction. So this whole idea of a reaction, there are two parts to it. Okay. And both of them are in place at all times. Okay. So there's the kinetics, in other words, how fast does a reaction go, and the thermodynamic favorability, which goes to this delta G. So both of them are high, the reaction will go very fast. For example, when you light a match, oh, that phosphorus on that red phosphorus on the end of that match goes very fast and it's highly favored. So the delta G is very low. I mentioned a couple lectures ago regarding who's spelling the charcoal, by the way? Charcoal and diamonds. Okay, so charcoal is favored. That means its delta G is lower than the delta G for diamonds. So that means it's thermodynamically favored. However, the kinetics is very slow. The activation energy is extremely high. So this happens, your precious diamond will eventually go to carbon, but it'll happen very, very, very slow. So anyway, so this relationship is, if you're a chemistry major or a chemical engineering major, something like that, you will take a whole semester class on thermodynamics, and you will know this relationship very, very well. Okay. So this whole thing about delta G and kinetics applies to our living body. And that's where enzymes comes into play. They affect the kinetics part of this relationship. And since they're catalysts, they lower the activation energy. Okay, this is a graphic relationship of this delta G. Now they call it free energy. It's really Gibbs free energy, but anyway, free energy. And okay, so the height of that activation energy vector determines how slow or fast the reaction proceeds. This here so reading this graph, you look at the free energy difference, delta G, and the height of the activation energy. Now, theoretically, you covered all this in 305. And either you forgot about it, or it's been a long time, or you never learned it at all. It wasn't covered. Because I don't teach 305, so I'm not sure whether this is covered or not. Okay. So non-spontaneous, positive delta G, spontaneous, negative delta G. Those relationships are really important. Delta G is measured in kilocalories per mole. And this reaction here, we have, this is glucose or another hexose with lots of oxygen. This would be excess oxygen. Produces carbon dioxide and water and gives off lots of energy. And energy is released slowly and stored in triglycerides, glycogen, and proteins. Now, if you reverse the reaction, this changes sign. It becomes positive if it's going the opposite. And that's the energy is derived from the sun. Energy is required. Now, biochemists use the term pathway a lot. Basically, it's a series of reactions. That's all it is. Looking at our chart we had at the beginning of the semester, that was a biochemistry class. They'd be calling that a pathway chart. And these pathways get quite complicated. I remember in my classroom up in Tacoma, I had this huge chart on the wall with at least 600 or 700 pathway reactions on it. With, you know, it gets really wild. Okay, let's see. All right. When we talk about glycolysis, eventually, either today or the next lecture, this is the second step on glycolysis. The first step is to create the glucose 6-phosphate. So the second step is converting the glucose to fructose with a isomerase. And then this is with a kinase down here, because we're adding a phosphate group. Okay, notice that this requires energy. It's positive. It gets it from taking an ATP molecule and pulling off a phosphate. So it goes, and this gives off energy. And that energy is where that reaction gets its energy from the ATP to ADP reaction. This reaction is more favored still requires energy though. Now this exer, think of the exergonic reactions is an exothermic reaction, means it gives off heat. Endogonic reactions require energy. Yeah, I'll look into getting more worksheets. Okay, let's see. Everyone, as a big time review, difference between these type of cells. Eukaryotic cells are much more efficient also at creating energy than these guys. So these are very usually, low cellular count organisms down to single cell. Okay. Again, this is biology related. Okay, a lot of the stuff we're going to talk about in this chapter and the next chapters is mitochondrion focused. And what I mean by that is that's where all the reactions for creating energy and interconverting energy, etc., happens. Which is summarized here. Okay. We're going to talk about in a minute here the three main parts of energy generation. And the citric acid cycle is the middle one. The first one is glycolysis, second one, citric acid cycle. Sometimes it's called Krebs cycle. And then the last one is oxidative phosphorylation or electron transport. Those are the three main. Okay, so we convert a DP to a TP. And this kicks out carbon dioxide molecule. And I'm going to go into extreme detail and all this stuff here. Okay, the biology part here, I'm not focusing on at all. There are two processes that go on: catabolism and anabolism. This one takes or breaks down molecules. Principally glucose or glucose obtained from glycogen or triglycerides or protein. Those three are catabolized for energy. So metabolic pathways break down molecules via enzymes. And each of these steps is considered part of a pathway. Usually pathways are you have a substrate, you start with a substrate, and then you go to a product. And one to many steps. This makes up pathway. But it can be one step or it can be many steps. Bottom line in this. Okay, so this is breaking down, and this is building. And those two are commonly found. For example, there's something called neoglucogenesis. What that means is you're creating new glucose molecules. Okay, so that would be an example of, for example, if you took a triglyceride, broke it down, many steps. Ended up storing the glucose created in the breakdown of the triglyceride, storing in glycogen. That would be an example of anabolism. Catabolism, you would do to that many steps, but that's what you end up doing. So that would be breaking down. Okay, so these two are used extensively in biochemistry. So this is breakdown, buildup. And energy can be on either side. Okay, so food supplies these guys, and then these guys via pathways give off carbon dioxide, water, and ATP. Okay, we're going to talk about glycolysis here in a minute. And the purpose of that is to produce pyruvate. And that can be used in many directions. If it teams up and creates acetyl-CoA, that can then enter citric acid cycle, or it can be used by bacteria, fungus, yeast, that do not go through the citric acid cycle. Amino acids, there's a whole amino acid set of pathways to get here. Same with this here. So all three classes of quote unquote foods for complicated multi-cell organisms, the end goal is acetyl-CoA. So that acetyl-CoA then can enter the citric acid cycle, producing ATP. And then that product can then go on and get oxidized big time and produced ATP and water. And this requires oxygen. So that's the oxidation process. Hence the name oxidative phosphorylation. Okay, so the phosphorylation is taking ADP to ATP. And it's an oxidative process, so there's a transfer of electrons. And the oxidating agent is oxygen. So this is the process. 3 steps: glycolysis, citric acid cycle, and electron transport chain, which is sometimes called oxidative phosphorylation. Probably electron transport chain is more common, but frequently they're used together. Not so much digestion, enzymes. So proteins are done. The proteins, fats, and carbs. Small intestine. Stomach does proteins, and saliva does carbs. Okay, it's this acetyl-CoA production. That's done in the Krebs cycle is an older term you'll see depending on what you're reading, or you'll see it in biology books. And acetyl-CoA then goes on this is the acetyl part. It's a thiol. And this is a giant molecule called coenzyme A. Okay. There are these guys are redox molecules. And this is the reduced form. There, for example, NADH, the oxidized form is NAD plus. So when this is reduced, in other words, it gains a hydrogen and ends up going to that form. And I'm going to show you this as this evolves. So the idea is to make reduced coenzymes. So these are the reduced coenzymes. Because those are later used in the third pathway, which is this ATP production. And those are oxidized. Like I was just showing you. And during that oxidation process, there's a transfer of electrons, and hence the name electron transport. Okay, which is here, which we just talked about. Okay. So where this is going, this here, I'm not sure your question. So do we work on report sheets for next lab? You'll answer the questions, the pre-lab and post-lab questions. Is that what you mean? Since next week we're not having a wet lab, you're not having a pre-lab for next week. You're having a pre-lab for the last lab the following week. That's the last week of November. Okay, so the point of this question has to do with everything So that's lipids, proteins, and carbs. Acetyl-CoA. So that's the common point they're talking about here. And then, so this is the, this should be stage 2, by the way. So this is the, and then that goes to electron transport. So everything's funneled to get to this acetyl-CoA. And from there, it goes into citric acid, and then from there, electron transport. Yeah, so it's a citric acid cycle. Okay. Okay. Let's just explain the process. Now, you need to know this process, by the way, just FYI. You probably already know it from your biology classes and what we've covered so far. This whole concept of digestion. Okay, let's just explain what we talked about. Okay. All right, so this is adenosine triphosphate. Adenosine is a, there's a structure of it in a minute. So adenosine triphosphate has 3 phosphate groups. Adenosine diphosphate has 2. Basically, so these are phosphoric acid esters. So when one of those is lost, it goes to ADP and gives off a lot of energy. So that's how one of the ways the body stores energy is in creating ATPs, so it can be used later when energy is needed for pathways. That's what I just said. All right. So this is what the adenosine looks like. So you've got this. This is a form of ribose. And the main difference is this guy here. Instead of being a hydroxyl group, it's attached to this molecule up here. This heterocyclic nitrogen molecule. And these are esters. And they can be hydrolyzed when this bond is broken, and it becomes ADP. And when it's hydrolyzed, it gives off lots of energy. So it's thermodynamically favored. That means it gives up its phosphoric acid easily, and gives off energy as well. Making ATP is not favored because the delta G is positive, hence it requires energy to make an ATP. So this is concisely what we're talking about here. So whenever we need energy, we take an ATP and hydrolyze one of the phosphate groups off of it, generating a phosphate group. And that releases energy. To make an ATP, going this way requires energy and a phosphate group as well. Now, one of the reasons it's perfectly suited is because this can take place at room temperature or body temperature. Probably more accurately, let's just say body temperature here. It's not a high temperature process, frequently associated with energy type molecules like TNT, gunpowder, that kind of stuff, which involves energy transfer as well, but at very high temperatures. The other good thing about it is it's released with appropriate enzymes. Okay, and another thing about this, it can be regulated. For example, if you have low blood sugar, okay, there's a feedback loop in your body that says we need more glucose. So there's energy is required to do that. So it's regulated to release those enzymes or to activate them allosterically. And for example, in the glycolysis cycle, the first two steps of glycolysis are regulated by reverse feedback loops, saying that we need ATP. Body's telling that pathway, we need ATP, we're low on ATP. So what happens is enzymes are turned on that create and start the glycolysis process by taking glucose through a kinase, putting a phosphate group on carbon number 6. The second step is putting it on carbon number 1 and 6, and then it's converted to fructose. So it starts the glycolysis cycle. And then from the glycolysis cycle, it goes into citric acid cycle, and from there electron transport, producing a whole bunch of ATPs. So this is really important that this process, one, because it's done by enzymes, two, it's done at body temperature and can be regulated. Those are three important deals on production of ATP. Okay, okay, so these the first three steps of glycolysis. You're putting this the first step is glucose 6-phosphate. The second step is 6,1 bisphosphate. Or actually, it'd be 1,6, not 6,1. This one is smaller than 6, and this is going to be, and then it goes to fructose 1,6-phosphate. Let's see. Now, whenever we have a series of reactions, the delta G for some. Okay, so we take the algebraic sum of the delta G's for each reaction. So some can be positive. Some can be negative. All said and done is we will get a delta G for the whole reaction. And that's what they're talking about here. Overall energy is favorable. In other words, delta G is less than 0. Okay. Enzymes require certain pH and certain temperatures to function. So the body then has to make sure that that heat required for the enzymes to do their job is maintained. So that's why some of the energy has to be spent in keeping the body warm enough for that to happen. So this first step is the phosphorylation of glucose going to glucose 6-phosphate, okay? Notice that's not a favorable reaction. But when we release a phosphate group from the ATP going to ADP, it releases more energy than is required. Hence, we have a net gain of -4 kilocalories per mole. And that's what they're talking about here. So there's a lot of reactions that are unfavorable, even with an enzyme. But as long as we couple it with the release of a phosphate group from the ATP, we can overcome that. Because this -7 kilocalories is pretty large. same thing here. We need to have a net of a negative delta G for this to work, okay? So when we're creating ATP, from ADP, it requires a fair chunk of energy. So that's why we have to make sure that we have the right reactions coupled with it to provide enough energy to overcome energy required to go from ADP to ATP. Now, this is another way. What they're talking about here is this curved arrow means that this reaction happens at the same time. So that means we have this happens at the same time. Now, another thing is this is very common in pathways. If you ever pick up a book, textbook devoted to biochemistry, you'll see lots and lots and lots of pathways, and a lot of them will have these little curved reactions going on. That's just a shorthand way of writing this down here. So the net of this is another reaction requiring a fair amount of energy, but when succinyl-CoA goes to succinate plus CoA, it gives off minus 9.4 kilocalories, which is enough to overcome the positive 7.3 kilocalories required to go from, and this is similar to ADP and ATP. It's another energy molecule. Okay, all right. We have a net of -2. So long as it's negative, it's favored. Okay, so this now the coenzyme we already talked about. One of them is NAD plus being reduced to NADH. Okay, this is because we have a lot of the reactions are oxidation and reduction. You have to have two reactions going on simultaneously at all times, no exceptions. So that's why you need, the body needs to have a lot of these FADHs and NAD pluses around. These are oxidizing agents, and they're also called coenzymes, because they work simultaneously with the enzyme to produce the oxidation reduction reaction. Now, again, whenever we have an oxidation reduction, and when things are reduced, we gain hydrogens. When things are oxidized, we lose hydrogens. So in this case, this is being reduced because it's this B goes to H plus. Here, this is being oxidized because we're losing hydrogens. same amount of H's are lost and gained at the same time. And in your 305 class, when you talked about single replacement reactions, you talked about oxidation reduction, theoretically. And that's what this is, the same thing. Only instead of electrons, we're talking about hydrogens now in biochemistry. These are particularly this one and this one. I've seen a lot. Those are the most common two. And notice the difference between these two is reduced form has H's. And the oxide form is missing those H's. Normally we talk about loss of hydrogens, addition of oxygens, but particularly the loss of hydrogen, or the gain of hydrogen. And always, no exceptions, when an oxidation occurs and gives up electrons, you have to have something to receive those electrons. So if you look at this here, we have a CH3. When a methyl group is oxidized, it becomes an alcohol. When that alcohol is oxidized, it loses that H. When that aldehyde loses or is oxidized, it goes to the acid. So we're gaining oxygen, losing hydrogens. And when we produce energy in the body, it's an oxidation reduction process. So there's a lot of those going on. Okay, so again, we have this NAD plus to NADH, NADP plus to NADPH. Okay, so this is the oxidized form, reduced form. Okay, so this is what NADH plus looks like. And this, let's see, how should I do this? This part is over here. Okay, so this version on the right has two more hydrogens than the one on the left, hence it's reduced. and good old ribose sugar. Two phosphate esters. Ribose sugar again. Okay, so NAD going to NADH is being reduced. Okay. So that means this has to be oxidized. Okay, so this gains a hydrogen. That means this loses hydrogens. Okay, so the hydrogens that are lost are these guys here. So it's going to be, let's see. So that secondary alcohol is converted to a carbonyl group or a ketone. Now the name for this is malate, and it comes from malic acid, or it is a 1, 2, 3, 4. So it's a and 1, 2, so it's 2 all. 1,4 butadioic acid, or that would be the official name for that, or malate. Okay, this just summarized it. Let me just went to up there. So whenever we lose hydrogens, we're losing electrons with them. Okay, so this means this is being oxidized because we're losing electrons and gaining hydrogens. Same thing here. So the one on the right, the NADH, has gained a hydrogen. That means it's being reduced. So this is receiving electrons. Okay, so that means that this thing is being reduced. So this is a oxidizing agent. Which means it causes oxidation because it's being reduced. So something needs to give, the one on the left here, the NAD plus, needs to give it electrons. So that would be an oxidation reaction. So the weird thing about oxidation reduction is an oxidizing agent the G, by the way. An oxidizing agent is being reduced. A reducing agent is being oxidized. A lot of students get really confused on those. FAD, HQ, same thing. So what's happening? Notice ribose again. Ribose is used all over the place in our body. Okay, looking at this guy here, okay, these two nitrogens have no hydrogens. These two hydrogens on the right have gained two hydrogens. Hence, the FAD is being reduced to FADH2. Again, gaining hydrogens, reduction. Now, electron carriers means they've received electrons. And gained hydrogens. Okay. What I want to do is stop here. And because this is going to get into all the reactions of the citric acid cycle here. And I want to talk about glycolysis first. So that's where I'm going to start the next time we meet, is on glycolysis, which is chapter, well, it's a chapter labeled, we put it this way. Carbohydrate metabolism in your book. No, that's my chapter 22. It may not be your chapter 22. Depending on what version you have. Okay, so again, we're going to pick up, this is the second part. I'm going to do glycolysis first because that leads us into reading that. So glycolysis gives us acetyl-CoA. Now from acetyl-CoA, we're going to start the cycle. And the cycle is going to give off carbon dioxide and then lead us into the third stage, third part, electron transport. Okay. All right. Now for Wednesday lab people, at the beginning of the 3 o'clock, there's going to be a woman coming in that's going to give a student survey out. Her name is Dr. Hutton, and she's the Dean of the Natural Sciences Division. That means physics, geology, astronomy, chemistry, all those divisions, all those departments are under her. She's going to be giving out the survey. So try to be on time. I know sometimes 5 minutes go by, 3:05, and people start struggling, but be on time today because it's she's going to give out the survey, and she's a very, very busy person. So I'd appreciate it as a favor to me to be on time today. Okay. The lab is pretty, most people on Monday like the lab. So it's a nice lab. It's very straightforward. Make sure you focus on that flow chart because you're going to be given an unknown today. And at the end of your time at the lab, I can tell you whether your unknown is correct or not. Okay, so any more questions? Okay, well, I'm gonna end it here and I'll see everyone at 3.
Bye, Professor.
Bye.